So we are continuing to look at techniques of taking the derivative without using the formal definition anymore, unless we are asked to use it. At the end of the last class period, we looked at the derivative of the quotient rule. We proved how we came up with this. So in front of us is just a reminder, the quotient rule, taking the derivative. And also in front of us is a little bit different notation that is used than what I had written out yesterday. And so let's just go through this and then we'll get a chance to apply it with some examples. So the derivative of the quotient of two functions is given by what is called the quotient rule. So this tells me if u and v are both differentiable at x, and if our function v of x doesn't equal 0, then the quotient rule u divided by v is differentiable at x, and if we took the derivative of this quotient d dx of u over v, this is what it's telling me. So it says v, which is our original function in the numerator, of the denominator. Sorry, b is in the denominator. So it's our original function, and this du dx, this is telling me I'm taking the derivative of my numerator, u, minus, I'm going to look at my original numerator, u, that function, times the derivative dv dx. So taking the derivative of v with respect to x. And this is all over the denominator squared. So function notation, and this is the way I had kind of written it. I just used y equals f of x over g of x yesterday. So I said let y equal f of x over g of x. And then if I look at the derivative, y prime, this is just saying I'm taking the derivative of my quotient f of x over g of x and taking that derivative that is equal to, and I said the derivative of the numerator, f prime of x, they just have f prime of x second, times the denominator, g of x, minus the numerator, f of x, times the derivative of the denominator, g prime of x, all over our denominator, g of x, quantity squared. So I suggest the product rule and the quotient rule, you memorize those. You're going to be using them a lot. And so you might want to make some flashcards and have, the product rule, f of x times g of x on one side, and then the derivative, that rule of the derivative of the product on the other side. And same thing with the quotient rule. Okay, so let's look at some examples using what we've learned so far, using that general power rule and the product and quotient rule to find derivatives of functions. So our example in front of us now, we're given this function z, and z is equal to f minus 3 of x. That quantity is in our numerator, all over the quantity 3x squared plus x. And it's asking us to find the derivative of z. So there's different ways that we can write this. We can find z prime, or dz over dx. Okay, so we're looking at the derivative of the numerator. So I'm going to not do the derivative yet, but you can if you want. So the derivative of the numerator, which is this 4 minus 3x, all times the denominator. And my denominator is 3x squared plus x. minus my numerator, which is this 4 minus 3x, all times the derivative. So I'm going to write that as dx. I'm going to take that derivative, haven't done it yet, of the denominator, which is 3x squared plus x, all over the derivative of the denominator. I'm not derivative of the denominator, I apologize. All over the denominator quantity squared. Okay, so now let's go through and actually do what we were saying. So let's say we want to take the derivative of this numerator. So remember, the derivative of a constant is 0. So the derivative of this 4 is 0, minus the derivative of 3x. Well, the derivative of 3x is 3, so minus 3. So that's in parentheses, times the whole denominator. So I'm just going to rewrite it, 3x squared plus x, minus my numerator, or minus 3x, all times the derivative of the denominator. So let's look at this piece. So the derivative of 3x squared, bring our power down front and multiply it by the 3. So we have 2 times 3 is 6x, and subtract 1 from our exponent. So that just gives me a 1, plus the derivative of x, which is just 1, all over the denominator quantity squared. So 3x squared plus x quantity squared. Okay, so we want to expand and combine like terms. And so if we distribute our -3 here in the numerator to that parentheses 3x squared plus x, well, -3 times 3x squared, that gives us -9x squared. -3 times x, so that gives us a minus 3x, minus, so I'm going to distribute here. So 4 times 6x, that's 24x. 4 times 1, that's plus 4. -3x times 6x, so that's minus 18x squared. -3x times 1, so that is -3x. And I'm going to keep this. I'm not going to expand the denominator because I might want to simplify it. So I have -9x squared minus 3x minus, so combining like terms in the brackets, I'm going to rewrite it descending order of power. So I have a -18x squared. Here I have a 24x minus 3x, so plus a 21x plus 4, all over 3x squared plus x quantity squared. So we still have this negative out front of that bracket from up here. And so we're going to distribute it to each term inside that bracket, and then we can combine like terms in the numerator. So you have -9x squared minus 3x. Distributing my negative, -1 times -18x squared is plus 18x squared. Minus 21x minus 4. All over this denominator quantity squared. Almost there. So combining like terms in the numerator, we now have a -9x squared minus 8 or plus an 18x squared. So that's going to give us a positive 9x squared. Then we have a -3x minus a 21x. So that's going to give us a minus 24x. And then minus 4. All over 3x plus x quantity squared. And so I'm just looking at this to see if there was anything that we could factor and that would cancel with the denominator. And I don't think there is. So I would just leave it like that.
Wait, isn't it 3x squared plus x quantity squared?
Mm-hmm. Yeah, right here. The squared right here. And so I don't think that that though cancels with anything that's up in here. I could technically factor out an x from both
But
of those.
isn't it 3x squared, not just 3x?
Oh, thank you, thank you, thank you. This is what you were talking about, not the one out there. You're right. So we could technically factor out an x, but that's not gonna, I don't think, cancel or with anything up above. And I don't think that this factors to have a 3x plus 1 as a factor. So I'm just going to leave it alone like that. And so that is our final answer. That is our derivative of z using the quotient rule. Okay, so our next example, we have w as our function and w is in terms of x, and w is equal to quantity 2x minus 7. That quantity is raised to the -1 power, and that's all multiplied times x, that quantity x plus 5. And we want to find the derivative. So another way to write this is the derivative of w with respect to x is dw dx. Right now, the way this is written, we don't know how to take the derivative. In the future, in a couple more sections, we'll learn the chain rule, and we can use the chain rule plus the product rule. But we don't know the chain rule yet, and so we don't know how to take that derivative of 2x minus 7 raised to the -1 power. So we could rewrite this and then use the tools we know to find the derivative. And so recall, we could rewrite this, rewriting 2x minus 7 to the -1 with a positive exponent. We can bring that down to the denominator and make that positive. So I'm left with x plus 5 in the numerator all over 2x minus 7 in the denominator. So now it's in the form that I can use the quotient rule. So I'm just getting you used to again how to write all of this. So the derivative of w, or the derivative of w with respect to x, is equal to d dx. That's telling me I'm taking the derivative of this piece, x plus 5 all over 2x minus 7. Which means I need to use my quotient rule. So if I look at the derivative of my numerator, all times my denominator minus my numerator, which is x plus 5, times the derivative of my denominator, which is 2x minus 7. That didn't take the derivative yet, all over my denominator squared. So now go through and take the derivative of each piece that we need to. So the derivative of our numerator, derivative of x plus 5, well, the derivative of x is 1 and the derivative of 5 is 0. So all we're left with is 1 times this 2x minus 7 minus my numerator, so x plus 5, all times the derivative of 2x minus 7. So the derivative of 2x, that's 2, and the derivative of 7 is 0. So we're just left with 2 for the derivative of the denominator, all over the denominator. quantity squared. So distributing one, I can just basically drop my parentheses on 2x minus 7. And let's think of this as distributing a -2. So -2 times x, so that's minus 2x, and -2 times 5, so minus 10, all over our denominator, 2x minus 7, quantity squared. So notice here our numerator, 2x minus 2x cancels, and we have -7 minus 10, so that's -17 all over 2x minus 7, quantity squared. Let's see if there's any questions, and if not, then we'll look at the easiest thing to ever take the derivative of, which is e to the x, function e to the x. Okay, so we've been looking at the rules. I just said that this was going to be the easiest one. So the derivative of e to the x, it's just e to the x. We've proved a lot of how we got these rules and taken the derivative by looking at the formal definition of derivative. The limit as h goes to 0 of that difference quotient of that function. I'm not going to prove this one. We're just going to take it for that it's true without proving it, just to save some time in class. But let's look at a few examples using this and some other rules that we had used or looked at so far. So if we have the function, let's say w is equal to x and all times e to the x. And we want to find the derivative of w. Okay, so I notice in here that I have a product of two functions. I have this x, and then I have this times e to the x. And so I know I'm going to need to use my product rule. And so let me just write it down. The product rule said, remember, take the derivative of the first all times the second, which is, so derivative of x all times the second, which is e to the x, plus the first, which was x, all times the derivative of the second function, so derivative of e to the x. So the derivative of w, the derivative of x, is just 1 times e to the x plus x times the derivative of e to the x, which is e to the x. We can leave it like this, or we're going to notice that a lot of times it's going to be helpful if we can factor out what they have in common. And so notice both of those terms have e to the x in common. So we could pull out an e to the x from that first term and the second term. We pulled it out of this first term. You're just left with a 1. Plus, and if we pull out this e to the x from the second term, we're left with that x. Okay, so I saw another example in your homework in this section, and I thought to myself, you guys haven't learned this, you need the chain rule. But then I thought about it. There's ways that we can rewrite our functions so that we can use the rules that we have. And so let's look at the case where you have y is equal to e to the 2 x power. We just saw that the derivative of e to the x is equal to e to the x. The problem is that I have this 2 in front of the x and the exponent. And so when we want to find that derivative, we can rewrite it. So let's use our rules of exponents. We can rewrite e to the 2x as e to the x plus x. And remember, when we added exponents, that was like multiplication, same base. And so here we're going to have, this is the same thing as y is equal to e to the x times e to the x. Kind of going backwards from what we normally would do. Normally we had multiplication, same base, we would add our exponents. Okay, so now knowing that, we can use our product rule. So our product rule says we're going to take the derivative of the first. Well, the derivative of the first, e to the x, is just e to the x times the second, which is e to the x, plus the first function, e to the x, times the derivative of the second function. Well, the derivative of e to the x, again, is just e to the x. Well, let's rewrite it. E to the x times e to the x is the same thing as e to the 2x plus e to the 2x. These are like terms. They're the exact same base, exact same exponent. We have 2 of them. So 1 e to the 2x plus 1 e to the 2x is 2 e to the 2x. So our derivative of y, e to the 2x, is equal to 2 e to the 2x power. Be careful, because some of your examples in here, they might trick you, because you might see this e. E, though, recall, is just a number. It's just an irrational number, 2.718. It just goes on the decimal infinitely without repeating itself. And so if, for example, you had, just put that down there. Let's say f of x is equal to 2 square roots of x squared, or actually x cubed, plus 3e squared. And it wants us to find the derivative. So I can write this, if I want, as f prime of x. So let me just rewrite this a little bit. That 2 square roots of x cubed, if we rewrite this in exponential form, getting rid of the radical, this is the same thing as 2x to the 3/2 power plus 3e squared. So now it's in the form that we can take the derivative. And so when we take the derivative, we have this 2 out front. We're going to bring our power down front times x, subtract 1 from our exponent. So I'm subtracting 1. Let's think of it as 2 over 2 to get a common denominator, plus the derivative of 3e squared. 3e squared is a constant. And the derivative of a constant, recall, is 0. So if I took the derivative of 3e squared, this is equal to 0. So cleaning this up a little bit, I had that 2 times the power I brought down 3/2. And so notice my 2's cancel, and we're left with just 3x, and 3/2 minus 2/2, that gives me a 1/2 power. And I started with a radical, so I'm going to rewrite that x to the 1/2 in radical form. So I have 3 square roots of x. So there's, when you see e, see if there's an x in that term or not. If there is, we need to take the derivative. If there's no x in there, then treat it as a constant, and we take the derivative of a constant, it's 0. So the last thing in this section talks about higher derivatives. So we can take the derivative more than once. So we can take the derivative twice, we can take the derivative 3 times, and there's applications where we may want to take the derivative more than once. And we'll look at that in a minute, but first let's look at the notation, and let's look at a couple of examples of taking the higher derivatives than just the first power. Okay, so in front of us talks about higher order derivatives and the second derivative. So let's just go through this really quickly. And it says if y equals f of x is differentiable function, so it has to be a differentiable function, then its derivative f prime of x is also a function. So we saw that the derivative of a function was also a function. So if that's true, if f prime is also differentiable, okay, so the derivative function also has to be differentiable, meaning that the derivative exists, then we can differentiate f prime to get a new function of x denoted by, right, we say f double prime. So f double prime equals the derivative of the derivative. The function f prime is called the second derivative of f because it is the derivative of the first derivative. It is written in several different ways. So we can use those prime notation, and d squared y over dx squared. Or this is saying we're going to take the derivative d dx of dy dx, which is saying the derivative of y with respect to x. Or we can use that prime with a dy, so dy dx, and take that derivative because that prime. Y double prime, I don't usually use these last two, but they're there just so for your notation. Same thing, just in case you're reading it, you know what it's talking about. So the symbol capital D squared means that the operation of differentiation is performed twice. So let's look at an example where we're looking at finding the derivative more than once. Okay, so the next example tells us that we have y equals x cubed plus 7 in the numerator all over x, and we want to find the first and the second derivative of the function. First thing that I was looking at was that a lot of times we can rewrite these to make them a little easier to take the derivative of. So notice I could rewrite that as 2 separate terms because I'm just dividing by one term. I could divide each term in the numerator by that x. If I did that, it might be a little easier because I could rewrite this as x cubed over x plus 7 over x, which reduces, right? That first term reduces. I have an x cubed over x, which is an x squared, plus 7 over x. So writing it this way, I can use my rule. So the sum of 2 functions, the derivative of the sum of 2 functions, which is easy, but also I would have to use here, though, the quotient rule. where before I would have to just use the quotient rule. So either way you can do it, and in the end you would get the same results. It might look a little differently, but if you rewrite them to maybe have a common denominator, and you would see that they're the same. So now that I have this, I rewrote my function of y. Let's take the first derivative of this. So dy dx. So if I take the first derivative of the first term, x squared, bring my power down front to, I'm using the general power rule, times x, subtract 1 from my exponent. So derivative of x squared is 2x plus, so I need to use my quotient rule here. So the derivative of the numerator, well, the derivative, I'll just write it, d dx, I haven't taken it yet, of 7.
Wait, why couldn't we just rewrite it as 7x to the negative 1?
You're right. I knew okay. You're totally right. That would be so much easier. And I was thinking I would have to do it the hard way with that quotient rule. So let's do what Ella said. That would make it so we don't have to use the quotient rule. So we could rewrite, making our exponent, we can bring this up into the numerator, right? And rewrite this as 7x to the negative 1 power. And now that we wrote it like that, now we can use our general power rule. So now if we bring our exponent down front, we have our 7 there times our exponent.
I think it's frozen again.
Yeah.
Darn it.
It's about that time, right?
I know. That's why I stopped it. Let me just, I think the easiest is me just like jumping out real quick and then coming back in. I think that's the fastest way to do it. Okay. I'm just going to pause it while I get everything back up. Okay, so we rewrote our 7 over x in here as 7x to the negative 1 power. And now we can use that general power rule, right? And bring our exponent down front of negative 1 times that 7x. And now subtract 1 from our exponent. Well, negative 1 minus a 1 gives us a negative 2 exponent. And so let's just clean up this first derivative really quickly. So dy dx is equal to 2x. Well, 7 times negative 1, so that's going to be minus 7x to the negative 2 power. I technically want to leave it like this just because I know I'm going to have to take the second derivative. And so taking the second derivative, it's much easier in this form than rewriting it and having to use that quotient rule. So let's look at the second derivatives. So that's saying I could write this as d squared y over dx squared. I'm just going and taking the derivative of my derivative function. So the derivative of my first term, derivative of 2x is just 2. And I have this minus 7. And I want to use my power rule again. So taking the derivative of this x to the negative 2 power, bring my power down front. So bringing down my negative 2 and subtract 1 from my exponent. So negative 2 minus 1 gives us a negative 3 exponent. And so we really have 2, well, negative 7 minus or times a negative 2. So this is really plus 14x to the negative 3rd power. So this is our second derivative. And if I wanted to, I could rewrite these without negative exponents by bringing that exponent piece down to the denominator. So this is the same thing as 2 plus 14 over x cubed. And if I want to kind of go back to what I had started with as a single fraction, I could even take this a little further and multiply that first term, 2 by x cubed over x cubed, getting a common denominator. And my answer is going to be 2x cubed plus 14 all over x cubed. Okay. And I could do the same thing with the first derivative, but I just kind of wanted to give you the idea that we can go about that and do it that way. We'll get practice of second derivatives. Basically, it's just taking the derivative of a derivative. So if you know how to take the derivative once, you should be okay with taking it more than once. Well, we'll get practice with that in a second, or not a second, tomorrow when we look at rates of change. But I wanted to look at one example, which I think you might help you. Oh no. Recording in progress. I didn't say, and I didn't record any of that. So if you were watching this video, we just went through this finding the equation of the normal line. We were given find the equation of the line perpendicular to the tangent line y equals x cubed minus 4x plus 1 at the point 2, 1. We needed to find the derivative that would give us the slope of the tangent line. Once we evaluate it when x equals 2, we can use our fast way of taking derivatives, general power rule. Derivative of x cubed is 3x squared, derivative of negative 4x is 4, derivative of constant is 0. So plugging in our x value of our point, we get back that our value there, the derivative of 2, is equal to 8. And then we found the equation of the tangent line. To do that, we find the equation of the line perpendicular. We had to do perpendicular slopes were negative reciprocals. So that gave us negative 1/8 as our slope to the normal curve. We had the 0.21, it was given to us. Plugging things in, we found b would be 5/4. And so our equation of our normal line is this. I apologize, I forgot to turn on the recording and class is over. So I just wanted to race through that problem for those who are watching this at a separate time. Okay, so that concludes this section.